Okay, we're going to be combining 1.3 and 1.4 in this video. 1.3 is about average rates of change, which I'll demonstrate first, and then we're going to get to calculus by taking a limit, and that's why we had to study limits. 1.3, don't bother with any of that homework. 1.4, there's just a few problems, and I only want you to do parts C and D. You don't have to graph or use a calculator or anything. Here we go. First off, average rates of change. Let's say we have some function f of x, and I have an x value which corresponds to a point on the graph, which has a y value. You should have learned all this in pre-calculus, by the way. The y value would be plug the x value into the function and you get f of x. Now what I want to do is let's say that represents your profits at some point in time x. And we want to go out a little bit. I'm going to say h units. That gives me a new x value, right? I started at x and I added h to it. And that has its own point, which corresponds to its own y value. And that y value will be where I plug in x plus h, a new number, into the function. Okay? So my x values are h units apart from each other. My y value will be the difference in the distance between the y values will be the difference between these two guys right here. And if I connect those dots, you'll see this again on a page coming up. If I connect these dots, these 2 points in time along this graph, this is called the secant line. And the slope of the secant equals the average rate of change. How far up did I go over this h period of time? Having trouble writing today. Average rate of change. And that's how much did this change over that span right there. How much did the y change when the x changed? And the way we find this is called the difference quotient. The difference quotient is just I can't write. Okay, difference quotient. The difference quotient is just the formula for slope. And the formula for slope is y minus y divided by x minus x. Now, I have to start at the same place. If I put this y value first, I have to start with that x value minus the second x value. But look at the bottom. I have x minus x. Those guys are going to cancel out, and I'm going to be left with just h. So I'm going to just erase the x's because they subtracted. And you see that my denominator is the distance between the two x values. This is my run, where this is my rise. So the difference quotient, just rise over run. Okay? The thing is, we have not numbers, not points, but we have a function. We have a starting place, and how far over we're going to go gives us the x value of where we're going to stop. This is the x value of the second point. And then what we're going to do is we're going to use any x value instead of a number, and we're going to use any distance instead of saying a particular number. This way we can find a function for the difference quotient, and we can plug in any x we choose so that we can see any possible outcome. All right, let's do an example for the difference quotient. We have this parabola here. So the difference quotient is we plug in x plus h in for each of these x's, then we have the function itself, and we're subtracting. All right? So what I need for you to do is to copy the structure of the difference quotient first. All right? You learned this in pre-calculus. So you have a particular structure of your function and a particular structure of the difference quotient. The difference quotient is a great big fraction, h in the bottom, and you've got a big function minus a big function. So that's what I always do. I just put the big fraction with the h in the bottom, and I put great big brackets with a minus in between. Then I go up here to my function, and for f of x plus h, instead of writing this with x's in it, I put parentheses. So I have parentheses squared minus 7 parentheses plus 5, and then whatever I'm plugging in goes in the parentheses here. Then I have minus big brackets. F of x is just the function. I'm just copying it here. If you do the structure first, this will make so much more sense and you're more likely to get it correct. Now, once I have this written down, I have to simplify it. And this blob squared is not just x squared plus h squared. It's blob squared is blob times blob. You have to FOIL this thing out. Don't be lazy. So you've got the first times the first. The outers and the inners both give you h times x, so you end up with two of them, and then plus h squared. So this bit right here, by the way, it's never going to change. It's always this right here. Anytime you have x plus h to the second power, you're going to get this in your problem. Probably by the time you finish your homework, that'll be second nature. Now we have minus 7 times the blob. I'm going to distribute the minus along with the 7. So I get negative 7x, negative 7h right here. Then I have the plus 5. But then this minus gets distributed to each of these pieces, and I end up with minus x squared plus 7x minus 5. Now, in pre-calculus, you learned that the same thing happens every time you do a difference quotient. Anything that doesn't have an h is going to subtract away. So all of these pieces back here are going to subtract pieces from up here. Notice in red I have minus x squared plus x squared. In the green I have plus 7x and I have minus 7x. And in the blue I have minus 5 and here I had plus 5. Everything else that's left has a factor of h. Make a list of what's left, and you'll see there's an h, there's h squared, and there's an h. So I can factor h out of this top thing. You're going to do this every single time. Every problem works the same way. Factor the h out front. I'm going to be left with a 2 times an x plus another h minus a 7. Now notice that because I factored an h out, I can cancel that h in the denominator, and I'm left with just this stuff. Okay, now you try it. Okay, and now that we've got all that down, we have arrived at the calculus portion. All right, let's say we have some function f of x. I have a point on my function. We're assuming, by the way, that our function is smooth and continuous on the interval that we're looking at. So that point has an x value and a y value, correct? Now let's scoot over a little bit from that point. We're going to scoot over h units. That gives me a new x value, which was the x where we started, plus h more. That has a point all of its own on our curve, and that point has its own y value. Now that's an h, okay. I'm going to zoom in here so we can see what we're doing. If we connect these dots with a line that passes through 2 points on a curve is called a secant. Now the slope of that secant gives me the average rate of change over that interval. So y goes from here to there over, imagine it's like these are your revenues for your company over a 6-month period, for instance. You can find the average rate of change over those 6 months by simply using the slope formula. It's the y value minus the y value divided by the x value minus the x value, right? y2 minus y1, average rate of change. That's pretty funny. Change, okay? All right, so y minus y over x minus x will give me the slope of the line. But look at the bottom, x plus h minus x. Well, the x's cancel, right? And we're left with just h in the denominator. Some of you will recognize this. You did it, or you should have, in pre-calculus. This is the difference quotient. It's the slope of the secant line, and it represents the average rate of change. Now, in the real world, average rate of change is great, but sometimes you need an instantaneous rate of change. So let's pretend that h shrinks down until it's a 0. So we want to take this x value and squish it down to here, which will take that y value, that point. Okay, h is going to go to 0. We're going to take this y, but that point is going to slide down as the x value changes until it is just 1 point on the graph. This line that touches the graph at a single point is called a tangent line. And the slope of the tangent line will represent your instantaneous rate of change. All right, so the difference quotient, this guy right here, gives you your average rate of change when h is not 0, because you can't divide by 0, correct? But we have a new tool. We have a tool now called the limit. So what we can do is find the instantaneous rate of change by taking the limit as h goes to 0, and that will give us what's called the derivative. Welcome to calculus. So the derivative of this function is the instantaneous rate of change, and it is also the slope of the tangent line. So there's a whole lot of information packed into this one thing. We call it the derivative. We have special notation for it. I'm going to introduce you to one type of notation now, and we'll get to the other type later. But the slope of the tangent, instantaneous rate of change. This is read as f prime of x. That's the way you read the notation. And prime is just, it's like an apostrophe. It's not an exponent, it's just a prime. And it's the difference quotient, but you take the limit as the h in the denominator shrinks down to 0. Now, if you remember from pre-calculus, the difference quotient, same thing happens every time you do it, right? Once you plug in the x plus the h and you subtract the f of x, all of the pieces that don't have an h in them get subtracted away. It works the same way every single time. So let's tackle it. All right, what's happening here is we're using this function again, and we're going to find the derivative. So f prime is the limit as h goes to 0. When you do these problems, I want you to do the structure of the problem first. Always write your limit because you need to know what you intend to do. It's a ratio, so you make a big fraction. The denominator is always h. You're going to have this first bit minus the second bit. Write down the structure. And the difference quotient says for the first bit, I'm going to plug in the x plus h for all of the x's. So we're going to do that last. Minus f of x, that's just the function. So you take your original function and you stick it in, all right? Just copy it. But the x plus h part, what you're doing, you're finding a composite function just like you did in pre-calculus. I'm going to take my original and I'm going to copy down the structure. Instead of writing h's, I'm going to put parentheses. So I have parentheses squared minus 7 times parentheses plus 5. And in the parentheses, I'm going to put x plus h. Right? So once you get the structure written down, now I have to do the algebra. So down here in my little thought type box here, I took x plus h. Squaring is not squaring the pieces. It's multiplying the entire thing times itself. You have to FOIL it out. Don't be lazy. So when you FOIL it out, you get this guy in the middle. So here is my f of x plus h. Here is where I distributed the negative 7. Don't forget to take the minus with the 7. Then I have the plus 5. Then I take this minus sign and distribute it through the f of x. And then I go back and anything that doesn't have an h gets subtracted away, right? X squared minus x squared, negative 7x plus 7x, plus 5 minus 5. And you'll see that it leaves me with just these bits, right? And all of these pieces have an h in them, which means that I can factor that h out. That's going to leave me with 2x plus h minus 7. And now, since I factored it out, I can cancel the h's. That leaves me with just the limit as h goes to 0 of the stuff that's left. And once I've divided away, canceled out that h from the denominator, now I can plug 0 in for the remaining h. It goes away. My answer is 2x minus 7. What does that mean? It means that at any point on this parabola, if I want to know the slope of the tangent, I can just plug the x value into 2x minus 7 and get that slope. Why is that important? Because the most important point on a parabola if you think about it here, is the vertex. And at that point, the slope is 0. So what you're going to do when you're finding derivatives is you're going to set them equal to 0, and you're going to get the most important values on your graph. They're called critical points, right? Okay, let's do one more. Let's say that we have f of x equals x cubed minus 2x plus 1. Now, the f prime is the limit as h shrinks down to nothing of the big fraction with h in the bottom. The first thing is where I'm plugging x plus h into the function. So I'm going to copy my function, but I'm going to use parentheses instead of x's. Minus, copy the function as it is. And that is minus f of x. And now, when I'm finding f of x plus h, this guy, that means I'm plugging x plus h in for each of those x's. I have my structure. I'm just writing x plus h. Now, on the last problem, we were squaring, and we FOILed it out over in the margin, and we're going to get the same thing every time we do that. X plus h squared is x squared plus twice hx plus h squared. But now I've got it cubed. So I've got another x plus h multiplying what I started with. And that's going to give me, first I'm going to distribute the x. You only need to do this once. And now I'm going to distribute the h through everything. And I'm going to get plus hx squared plus h squared x. There's a 2 there. Holding the phone, hold the phone, hold the phone. Right here, h times this guy gives me 2h squared x. And then the last times the last gives me h cubed. And again, you only have to do this once. This blob cubed is never going to change, right? H cubed, 3, the power of, sorry, that was x cubed. The power of x goes down 1 while the power of h goes up 1. Then I have plus 3 again. The power of h goes up to 2. The power of x goes down to 1. Plus 1. The power of h goes up to 3 when the power of x goes down to nothing. And that's important for you to notice for later. Okay, so now that I have my busy work written down, f prime is the limit as h, I always want to write x there, as h goes to 0, the big fraction with h in the bottom. The top is now x cubed, 3hx squared, 3h squared x plus x cubed. That's only the first blob. Next, I'm going to do, that was just this. Next, I'm going to distribute the minus 2 through here. I'm going to get minus 2x minus 2h. I have a plus 1. And now I'm going to distribute this minus through the parentheses. And I'm going to get minus x cubed, positive 2x, negative 1. And now the same thing happens every time. Didn't need those brackets there. The same thing happens every time. Anything without an h cancels. I'm going to start at the back because it's easier. Minus 1 cancels the plus 1. Positive 2x cancels negative 2x. Negative x cubed, positive x cubed. Now I'm left with that guy, that guy, that guy, and that guy. Everybody that's left has an h. I can't plug in the 0 to take the limit until the guy on the bottom gets canceled though. So I'm left with 3h x squared plus 3h squared x plus h cubed, and then over here I have a minus 2h. Got a little overzealous with my line there. Equals the limit as h shrinks down to nothing. Factor the h out of the top. I'm left with 3x squared plus 3 with an h left and an x, plus factoring h out of h cubed gives me h squared minus 2, and the h got factored out. And now, bang, bang, those guys are gone. And I'm going to do an extra step here at the same time. The limit as h goes down to 0 means that this goes to 0 and this goes to 0. I'm going to mark that in blue, where this guy becomes a 0, this guy goes to 0, and what am I left with? After taking that limit, I have 3x squared minus 2. That's the derivative of the original function up here. So if you graph this graph, then all of your vertices would be where this thing equals 0. And that's very, very important for you to be able to find where a graph changes direction. In other words, it has a vertex, and that's where your tangent line is horizontal. So you can find the x values of those vertices or those turning places by setting the slope of the tangent equal to 0. And now you're ready to do calculus. So the homework assignment was from 1.4. I want you to do 1 through 15. I think I wrote it on the front page. Parts C and D only. Part C is finding the difference quotient, and part D, finding the derivative, you're taking the limit of the difference quotient. And part D is you're going to plug a couple of numbers in there for the x's, like if I said for this problem, find f prime of 1. Then you would have 3, 1 squared minus 2. 3 minus 2 is 1. So that would be an example of your homework. Good luck, guys.